Here are practical insights about runtime audio codec switching and gaps on the Linux audio stack, by Rutvij Trivedi, from ADC Conference.
Brilliant. So we're now joined by Rutvij. I'm just bringing him into the webinar now. And just give me 1 second. There we go. Hey Rutvij, do you want to just turn your camera on and say hi to the audience? There you are. Brilliant. Hello.
Hey, hi. Hello everyone. How are you doing?
Brilliant. So you have a pre-recorded video, so we're just going to queue that up, but just wanted the audience to know you are here. So if you have any questions, post them in Discord, and you'll be able to respond live while the session is going. So thank you very much, and we're going to roll the video now. So I'll just queue that now.
Sure. Thank you very much.
Thank you very much. Just 1 second. I just need to realise I've hit the wrong button there. Let me just give it 1 second. There we go. And now we're going to cue the video in. There we go.
Hello everyone. I hope you are having a good day. Thank you for joining in my talk. Today I want to discuss a gap in Linux audio stack, runtime audio codec switching. This might sound like a very niche problem, but in fact it's extremely important for automotive age devices, where power, latency and safety requirement means you can just fix one codec and forget about it. Why? Is because cars don't have one uniform audio workload. They have dozens, each with very different requirements. A quick introduction about me. I am Rutvij Trivedi, the co-founder of Silicon Signals. Our team contributes to upstream projects like Linux, Zephyr, AOSP and U-Boot. Over the years, I have worked on products across consumer electronics, healthcare, IoT, audio, video, and especially automotive. In all of this domain, audio pipelines have been a recurring challenge to us. In fact, in one of my automotive projects, where I encountered this runtime switching problem, we had a SOC running a high-quality infotainment audio, but at the same time, the hardware had to support an emergency e-call. We realized that either we wasted a lot of power or we risked safety compliance. That's what it motivated me to dig deeper into ALSA internals. Now let's look at why automotive is different. Take infotainment as an example. For music streaming or video playback, you want Opus high quality and high bitrate codec that might consume around 25 milliwatts of power, but it delivers expectation on the audio which passenger expects. But an emergency call, at the same time, it requirement flips. You need something like G729, which is a low power and low latency, only about 5 milliwatts. It's not about quality anymore. It's about fast and reliable communication. If SOC always runs on Opus, you are wasting precious energy. If it always runs on G729, you are sacrificing audio quality. Now clearly we want a runtime switching to move codecs seamlessly depending upon this situation. But we'll see that Linux doesn't allow us that. Here is how the Linux ALSA is currently available. From user space, you open a PCM device and call sound PCM hardware params. That request will travel through front-end handler into DPCM BDI hardware params and finally into sound SOC DI hardware params. At this point, the codec driver programs the register and now the driver codec is fixed. If you need another codec, ALSA forces you to stop the current stream and reopen it. That means 100 millisecond of dropout and CPU spike. And in car, especially in emergency system, it's not acceptable at all. Of course, people have tried workarounds. Let me walk through them. User space transcoding. You decode in one codec, re-encode in another. That works but burns CPU cycle and drains a lot of battery. In vehicle with dozen of other real-time tasks, this is not suitable. Second is multiple ALSA devices. You expose multiple PCM device per codec. The problem is the choice is made at open time. There is still no runtime switch and application gets locked in. Third is restarting PCM stream. Yes, you achieve a switch, but only by tearing down reopening the stream. That gives 100 millisecond of gaps. Now imagine that is happening in the middle of an emergency call. where driver is talking to an emergency service. Completely not acceptable, and it's unsafe. So none of these hacks are meeting the automotive grade requirements. So what would a real solution look like? I see 4 building blocks. This is a proposal from our side, an ALSA control interface. This exposes standard control where user space can request codec not just at stream time but in the mid of the stream. A power scheduler in the kernel, which is a decision making engine that takes into account battery, network and safety priorities. Triple buffering in SOC drivers, so we call a shadow buffer. One codecs will drain, another codecs will start. And standard Linux device trees, so we can capture hints like power consumption and priority at standardized way across all the SOCs. These are not trivial but at least realistic extension for what currently ALSA is doing. This is a code snippet. So now let's put it all together. On the left we do have inputs like battery, network state and safety priorities. Inside switch there are 2 components we do have. One is scheduler, which decides when to switch, what to switch. The shadow buffer, which overlaps PCM frames, so one codecs drains down while other starts. On the right side we do have actual codecs. Opus for high quality, G729 for low power and PCM for latency. The key point is the scheduler makes a decision and shadow buffer makes it seamless. This is how we move from 100 millisecond of gap down to sub-frame transitions. Here is how code might look like. In kernel, we define an enum that gives controls to user space to pick codec, and behind the function like scheduler codec switch, it triggers transition. A prepare function feeds shadow buffer, and at safe boundary we swap the DMA pointers. This is how a device tree might look like. We describe each codec with its power and priority. For example, power Opus will require 25 millivolts of power with 2 priority and G729 for 5 millivolts with priority 1. So now these are not full implementation, but these are the sketches. ALSA could evolve on top of this in a structured and clean way. So what we can gain out of it? Dropout will reduce, like from 100 millisecond to 100 frame boundary, 10 to 20 milliseconds. Low CPU usage compared to transcoding or restart methods. Battery life, since now ecosystem of codecs have become intelligent. And importantly, we are achieving safety compliance as well, where reliability is critical. Now I'll be clear that these are not the actual projected number, these are just measured with the ALSA ground and buffer analysis. Of course, this is not an easy task, let's be honest. The problems are synchronization. You might align the exact frame boundaries, otherwise you risk click or loss samples. Codec state management, all these codecs will have their own context, and preserving those states will be during hot switch will be complex. Framework changes, ALSA and SOC PCM operations were never designed for this switch, so we'll need some kernel APIs and device trees. Fragmented SOC ecosystem. So Texas Instruments, NXP, Qualcomm each has different DSP IPs. Getting consistency across all the vendor is tough. User space policies, system like Pipewire and Android Audio HAL needs to cooperate with these changes, otherwise kernel changes won't be useful for us. These are significant challenges. So what is a roadmap look like? First, we'll need a kernel prototype to validate the shadow buffer and switching logic. Then we extend codec topology to support in ALSA, so multiple codec can be described in standard way. Third is policy integration where Pipewire or Android HAL, so switching decisions are actually useful in real time. And finally, talk to maintainers and do the upstream in ALSA. Now this is a crucial, because unless this might standardize, we'll end up with fragmented vendor specific solutions. This is not solved problem, but it's an opportunity for collaboration across community. So now we are here at the end of the presentation, and I'd like to summarize that today we discussed that Linux does not allow real-time codec switching, and that is a real blocker for automotive. Imagine a EV What we have outlined how ALSA could evolve with a scheduler, shadow buffer, and codec profile in device tree. It's challenging, but it's achievable. And more importantly, it's worth it, because this now is not about just a performance. In safety systems like eCall, it makes the difference between reliable connections and failed one. So I'd like to invite community people to come forward, analyze, plan, execute the next steps together. I hope you have enjoyed the presentation. Thank you very much for having me today. Bye-bye.
Working on Linux audio pipelines or automotive audio systems? Let's connect at info@siliconsignals.io.